to kind of, you'll see the same material, but it will be different questions. And my other classes, what I've done for astronomy and physical science is I will like take my old test questions and put them on a final, but that's not what I do for chemistry. So I think I mentioned yesterday that your chemistry final will have a multiple choice section and a short answer section. And for your final, you can bring a piece of paper, full piece of paper with notes on it. Okay. But it has to be handwritten, can't be typed. The problem I've run into with typed is you wouldn't, but they type it up and then they just give their friend a Xerox copy. So you have to do it yourself.
What if I promise not to do that? Is that would make the font like size like
But you can hire somebody that has tiny little writing to do your writing. Which kind of defeats the purpose a little bit because so handwritten. So before we pick up where we left off, and we're only gonna, this shouldn't take us all that long, but you never know. I was gonna show you a few things. There's all sorts of resources out there on the internet. This is why you can't have your smartphones while you're taking the test in here. Because as you might imagine, you know, there's all different, these electron configurations we've been coming up with, how electrons are hanging out, there's, how do I say, it's very kind of cut and dry. For instance, we talked about the abbreviated rare gas notation, and for, you know, oxygen, you take helium. Beyond helium, you have 6 electrons, where are they? 2s2, 2p4. Okay. So there's that. And then the other side, the other thing I wanted to show you, I think we've, I've taken here before when we talked about periodic table. It's just called p-table, ptable.com. And there's tabs along the top there, and there's a tab called orbitals. So you can click there, and you can see, like this is the, like for instance, if I picked on chromium, is that a good example? Well, let's pick on titanium, that's better. So 22 electrons around titanium. Here they are, here's the electron configuration. We kind of peter out in the 3D subshell with 2 electrons. And then I thought this is fun. If you click on any one of these electrons, it will give you the address. It'll give you the L value, the M sub L value, the N value, okay? And it'll give you a picture of it. That's electron output. So like if we know that the S's are all spherical, so there you go, there's the spherical ones. The P's are dumbbell shaped. Of course, we have 3 different, the P sub X, P sub Y, P sub Z. So I just think that's cool. Anyway, so yeah. And the arrow diagram is your friend. Again, you don't have to draw it for your next unit exam, but if you want to draw it, an advantage to drawing the arrow diagram and then using it is if you make a mistake on the arrow diagram, then I can kind of go back to what you were using and give you maybe partial credit. So of course you recognize the subshells. We max out at 2 electrons here, 6 electrons here, 10 electrons here, and 14 electrons here. And we completely fill the subshell until we completely fill the subshell before going to the next subshell. So this is kind of one thing I want to talk about. In addition to the arrow diagram, there is this kind of taking the periodic table and chunking it up and using it to your advantage to come up with electron configurations. So these guys right here, these are what we call the S block elements. So as you're finding homes for electrons, the last place to find homes for are going to be in S-type subshells here. Like for instance, I could go to barium, okay, and barium is in period 6. So actually, I could go, let's see, what's beyond? I could go Xe for xenon in brackets. I could go 6s superscript 2. That's how that works. Is that not slick or what? Those are S block. This is P block, kind of this in the kind of the pink sort of color over here. So you would hopefully tell me in any P subshell I can accommodate 6 electrons. Not so surprising, there are 6 groups in the P block. So for instance, if we pick on gallium, gallium is the first element in the P block for this period, which is what, period 4. So I am petering out with 4p1 electron there. So if we pick on gallium though, we know that it goes through what we call the inner transition, or the transition elements, okay? And these are D block. So D, you would tell me 10? There are actually 10 columns or 10 groups here, okay? So if I go back, but notice that it's n-1, and when I say n-1, it's the period -1. I wish my little marker worked. I need to figure out why it's not working. So if we just pick on gallium, gallium is in period 4. I would do argon because that's the rare gas before gallium. And then beyond argon, I look at my periodic table and I'm skipping through these 2 electrons. These would be 4s, 4s2. And then I'm skipping through period 4, this n-1 D block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 electrons, but it's not 4, it's 4 minus 1, or 3. So that's 3D10. And then I come across, I smack against the P block, and that's back to 4P1. See how that works? So we did S, P, D, and these guys are Fs. So there are 14 actually. Now, and these aren't N or N-1, they're N-2. So of course, this guy starting with cerium, they are stuck right here in period 6. So 6 minus 2 is 4. So we are populating 4 F electrons here, and we are populating 5 F electrons here. Now I'll tell on myself, when I start to get to these guys, I usually kind of go back to my arrow diagram because I get kind of confused. I don't want to get it wrong. So hydrogen, of course, has atomic number 1. That 1 electron is going to be in the 1s subshell, so it's 1s1. I don't know why that's there. Okay. Well, every rule was made to be broken. And so this arrow diagram, where I say you completely fill the subshell, then you go on to the next subshell, then you go on to the next subshell. When you fill a diagonal, you go on to the next diagonal. Well, this is where I'm telling you rules were meant to be broken, especially first starting with chromium. Chromium is a group B element, transition element. So if we look at chromium, we need to find homes for 24 electrons. So using the arrow diagram, which by the way, while I'm thinking of it, on your test, you're going to have to do electron configurations. Use the arrow diagram. The arrow diagram is applying the lowest n plus L rule. Use that, okay? So you guys would come up with this for chromium and you'd be done. That is totally what I'm looking for. Notice it peters out with 4 electrons in the 3D. If we want to go ahead and take those 2 electrons in the 4s and kind of show that they're valence electrons, we can unscramble that. That's in the order of increasing n. But instead of that, this is what chromium does. So let's kind of compare what we thought it should do with what it does. If you compare them a few times, you can kind of see these last 2 subshells. We have 1 electron that is actually going from a we have 1 electron that's going from a lower energy promoted up to a higher energy. So instead of 4s2, 3d4, we have 4s1, 3d5. So the catch here is if I were to ask you for any d-type subshell, you would hopefully tell me 5 orbitals. So this sweet sort of kind of resonance sort of deal happens because now it can have these subshells all half filled. Okay, so why do exceptions occur? Well, one of them is to get a half-filled subshell, like we saw with chromium, 5D, or the D5. One is to completely bump it full. Of course, for F, our subshell is half full if it has 7 electrons, okay, completely full of 14 electrons. So those are why exceptions occur. Was it my other class? I think so. But just know that I am after you to apply the lowest N plus L rule, not to do this exception stuff. But you need to know that they occur and generally why they occur. So by atomic number, of course, 24, atomic number 24, that's chromium. So 29 would be copper. Copper does it too, okay? The next period, you see several. And I found this site out there on the internet today too. I was getting ready for this class. So look for the exceptions. This is just another way to look at, okay. Oh, and I even printed it out for me. Right. But you can kind of see where there's chromium. Okay, so instead of just keeping the 4s filled, one of those electrons is promoted up. You kind of see this is copper exception. All right. So just to kind of finish, to wrap up this idea, this topic of electron configuration. At the end of each period is a rare gas. And elements want to get that rare gas configuration. Now remember that as elements pick up electrons to get the rare gas configuration, or if they're metals, they lose electrons to get the rare gas configuration of the, as it turns out, of the rare gas in the period before them, the heart of the atom stays the same. The protons and the neutrons, they stay the same. Electrons kind of come and go. But it's a very, very stable way electrons can be configured. Valence electrons, we already talked about. So for instance, in this case, the valence electrons here, the highest N is 4. So I'm looking at 3 valence electrons, 2 are the 4s and 1 is the 4p. And the reason that they're so important is those are the electrons that are either going to be kicked off if it's a metal, or actually those are the electrons that are going to be added to get that rare gas configuration if it's a nonmetal. So valence electrons, there are some times when you're going to want to look at a periodic table and you're like, how many valence electrons does that atom have? Well, if it's a group A element, remember group A element are S block and P block. If it's a group A element, the group number actually, which I don't like the group numbers here, will tell you the number of valence electrons. So the black and white periodic table like you guys have in your notes, you have like at the top of here, 1A, 2A. So 1 valence electron, 2 valence electrons. Skip the B's because it doesn't apply to the B's. This is group 3A, 3 valence electrons, 4A, 4 valence electrons, 5, 6, 7, of course, 8 valence electrons. Very good. Well, that's as far as I wanted to get today. So I told you. I know, you're like, really? So yeah. I will, that'll give me time to record going over the test, and I might even email you the link to the review video. Oh, homework? Anybody homework?
You didn't sign anything?
Yeah, we were halfway through.
Thank you. No homework due today. I hope you'll get your lab stuff graded and